And we're live.
There you go. Number 7, so in terms of a free body diagram, because I see friction and I see other forces mentioned here, we have gravity down, normal force up, here's the applied force, here's friction. So how much work will I do on the block? The key is, well, if it's at a steady speed, I've drawn friction wrong. I think friction is that long. So work equals the force applied times distance. I don't know the force applied. Oh, but look, 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 look. I know the force applied is the same as the force of friction, where friction is mu times the normal force. I don't know the normal force. Oh, but look, 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 look. I know another force the same size as the normal force. I think you're going to find, I hope, 0.4. Oh, you know what? That's not a mass. What is that there? That's mg, isn't it? Because it's Newton. That's a weight. So I'm just going to put 75. I don't need to multiply by 9.8. mg is just 75 times 4.2 meters. I hope that should be it. Yep. Any others? Sorry? Number 6? Okay. How much, 6a, how much work if you lift? So if you lift, work is almost always the force of gravity times distance. That g looks like it's in the equation. Make it a subscript. The force of gravity. When you lift, it's really mg, and traditionally in physics we call a vertical distance a height. So it's going to be 0.67 times 9.8 times 1.5. That's the answer to A. Okay. How much work will be done on the book if you lift it and move it 1.5 meters sideways to a spot on the same shelf? Well, there's 2 ways to think about it. This portion here is 0 joules. You're still doing 9.8. You know what happened? I think there used to be the word more there. I think the question used to say, how much more work will be done if you then slide it sideways? And the answer is none, because even though there's a distance, the force that you're resisting is vertical. Is that okay? It's a typo. I just caught that now. I'll fix that later. Work. If you have lesson 1 done, and many of you already did, hand it in. Let's jump to lesson 2. Normally, well, I'll try pausing the video, and let's hope that it comes back. Lesson 2, power. The English definition of power is the rate at which work is being done on an object. It's how fast you're doing work. Power, in terms of the way you guys think about it, actually equals tiredness. If you're exerting more power, Reed, that's what makes you more tired. It's the difference between walking 100 meters and sprinting 100 meters. Or better yet, for my track athletes, probably the most grueling event, walking 400 meters, walking 1 lap around the track, or sprinting 1 lap around the track. In one, you're exerting way more power. In fact, anytime we talk about the rate at which something is done, what we're really saying then is this. As an equation, it's work over time. Hey, what would be a good letter to use for power? Yeah. Power is work over time. It's how fast you're doing work. Thank you. We'll get some Timbits next class. Power your phone off. Okay, put it away. What are the units? Well, what's work measured in? Joules per. What's time measured in? So power is measured in joules per second, but we give that unit a special name. We call it watts, symbol W. Watts the unit for power? Okay. Power is a scalar. Well, of course it must be, because work is a scalar and time is a scalar. There is no direction when you're dividing them. How would you get power as a scalar? Measured in watts. It's named after a scientist whose last name was Watt, James Watt. James Watt is often credited with inventing the steam engine. He did not. He improved the steam engine dramatically right before the Industrial Revolution. I'm a little disappointed that he has a whole unit named after him, because he really didn't do that much, but what he was a very good promoter. We'll talk about that a bit later. So example, an electric motor is used with a pulley and a rope to lift a 650 Newton load. I guess 650 Newtons means they gave me the weight. They gave me mg, not kilograms. From the road up to a height of 12 meters. This job is done in a time of 11 seconds. What's the power output of the motor? Well, power is work over time. Power is work over time. What work? Well, work is force times distance over time. Force times distance over time. When you lift something, which force are you doing work against? Gravity, so it's really Fg times distance. Now normally I'd go mg, except here they gave me mg. It's just going to be 650. That is the weight. I don't need to multiply by 9.8 because they gave it to me in newtons. The distance we're raising it is 12 divided by a time of 11 seconds. How many watts of power are we getting out of this motor? 709 watts. Power in the metric system is measured in watts. In the imperial system, another unit is horsepower. As a matter of fact, this is the unit that James Watt invented. And this is why he was a good self-promoter. He's trying to sell steam engines, and he's trying to convince factory owners and farmers that they should buy a steam engine, but they have no idea how to put it in context. And so what he does, he invents a unit called the horsepower. He says, oh, this steam engine gives you 4 horsepower. Now, what does a farmer think? This steam engine does the same amount of work as what? 4 horses. See, now he's got a context. In fact, it was such a good unit, we still use it to talk about car engines, and none of us ride horses. None of us has any idea of what 1 horsepower is. Maybe if you live on a farm, maybe, but even then I doubt it. But hey, he was a good salesman. You know, car engines have 150 horsepower, 200 horsepower or more. So the motor in this example would have a horsepower of, oh, we want to do a conversion. We want to go from watts to horsepower. This is like from the very beginning of the year. Who remembers from the very beginning of the year how we always started out any conversion? What did we always do first? No, that was for forces. That was not from the beginning of the year. That was like from a month ago. From the very beginning, what did I always do? I wrote down what they gave me. And then I said, I want to multiply by some kind of a conversion factor. Now, right now, watts is on the top. I want it to cancel. So where do I want it in my second fraction? And I guess horsepower is going to be on the top. What's the conversion factor? 1 horsepower is apparently 750 watts. How many horsepower is this motor? It's going to be almost exactly 1. Because 750 over 750 would be 1. 709.1 over 750 seems like 0.98. Or what, how many horsepower is it? 0.95? So let's suppose in real life this motor was a 1 horsepower motor. It was capable of 750 watts. If you wanted to raise this 625 Newton load faster than 11 seconds, say in 5 seconds, the motor couldn't do it. It's impossible. It can do it slower, no problem. It can put out less power, but the limiting factor on how fast you can get the work done is the wattage that the motor can put out. So that's one place that this is used. A girl runs up a flight of stairs 3.32 meters high in 2.6 seconds. What's her power output? Okay, power is work over time. When you're going upstairs, which force are you doing work against? mg times the height, force times distance. See it there? Over time. What's her mass? 9.8 3.32 divided by 2.6. $751 watts. Almost exactly 1 horsepower. So I wrote B. If 1 horsepower equals 750 watts, what's her power output? That's the symbol for approximately 1 horsepower. Just to put that into context. So a 3.32 meter set of stairs, that's about 1 story. Walking a one-story flight of stairs in 2.6 seconds. So you would start on the bottom, 1,000, 1,000. That's probably going up a set of stairs a little bit faster than walking pace, maybe jogging up the stairs. Would that tire you out? Little. What if you sprinted up the stairs? What if you made time smaller? What would happen to this answer here if this number got smaller? Power would get? Would you be more or less tired if you sprinted up the stairs? More tired, okay? Or we do the other thing. For example, that hill way back there at the back corner of the field, that's a fairly steep hill. They've made pretty shallow stairs. Why? Because that forces you to take longer going up. You're not so tired at the end. It's for the, people that are out of shape or the older people. They could probably made it really steep and you kids could have handled it just fine, but you'd also be huffing and puffing when you got to the top. You're still doing the same amount of work. It's just how fast you do the work. Anthony, it's a difference between, I'm sure you've run at least 1 set of stairs in the back. Yeah, so it's a difference between walking that set of stairs and sprinting it. I'm telling you, you're not using more energy, just using the energy up faster. Okay? The horsepower was originally defined by James Watt, who was looking for a way to describe the power of his newly invented steam engines in terms that people accustomed to using horses to do their work could understand. I don't know how much he contributed to science, and the fact that I don't know suggests to me not much. I'm a little disappointed that he got this unit, because you've heard of watts, light bulbs, electricity dominates our society. We talk about many things in watts, right? Example 2, how long would it take a 10 horsepower motor to lift a 500 kilogram safe up to a window 30 meters above the ground? Oh, what's this question asking me to find? Let's use our DFIC approach. This is a little less plug and chug. What else have they told me? What's that 10? It's power. Are the units right, though? Okay, so let's go like this. Power equals, let's do our conversion. Right now, horsepowers are on the top. To get them to cancel, where do I want them in my conversion factor? Which means watts are going to be on, and it's 750 over 1. I hope nobody reached for their calculator. I hope everybody said, oh, 750 times 10. Okay, a 10 horsepower motor puts out about 7,500 watts. What else have they told me? What's that 500? What's that 30? Distance or height. Okay. Hey, is there an equation that has time and power in it? Now we need to get the t by itself. Ew. Where is the t right now? On the bottom, which is really the worst place. I think what we should do is we should times the t over to that side. Now it's on the top. And at the same time, how could I move this p over? Divide. Yet another equation that pops out of here. I guess time is equal to work divided by power. If you want to find out how long it's going to take you to do a job, find out how much work you're doing divided by what the power of your motor is, that's the fastest you can possibly do it if nothing goes wrong. Work is what times what? Force times distance. And then divided by power. It's going to be mg times h divided by power. And now we've got it to our relative plug and chug stage. M, 500. G, 9.8. H, 30. Power, 7,500. Minimum, how many seconds will this job take? Do you get 19.6 seconds? .6 seconds. Oh, by the way, 1 watt, not very big. We saw, for example, this girl running up the stairs was actually producing 750 watts, and that wasn't even running. So power on your electric bill is often measured in kilowatts, 1,000 watts at a time. Power, when you're talking about a hydroelectric dam or a nuclear reactor, often is measured in megawatts, 1,000,000 watts at a time. We're just starting to occasionally talk about gigawatts, but not very often. And have you watched Back to the Future, the movie? Okay. So he talks about something. He talks about gigawatts. He pronounces it wrong, of power that he claims they're getting. You are getting that much power from a lightning strike, lots of power, but they're gigawatts. Put your pencil down. Example 6, the power of, pick up your pencils. Power of a light bulb is the amount of electrical energy it consumes in 1 second. For example, a 40-watt bulb uses 40 joules of energy in 1 second. A 60-watt bulb uses 60 joules per second. A 100-watt bulb uses 100 joules per second. What's the power rating of a bulb that consumes 4,200 joules in 70 seconds? Well, power, work over time. How much work is being done? Well, work is measured in joules, so I guess, Rob, 4,200 divided by, and we've left the light on for 70 seconds. If these are the readings that we're getting from a smart meter, what kind of a bulb is this attached to? Does this work out even? 60, I think, is what I was trying to, is it 60? Yeah, 60-watt bulb. I'll go to 3 sig figs even. It's a 60-watt bulb. Well, certainly that means that using smaller wattage light bulbs does save electricity, does save energy. Fair enough. Why would we, what else could we do to save energy? Well, we could be more efficient. So efficiency means how much bang we get for the buck. In other words, how much energy coming out compared to how much energy we're putting in. There is a symbol for efficiency. It's sort of like a lowercase n with a tail. It's a Greek letter eta. Having said that, I didn't know that was the symbol for efficiency until about 4 years after starting to teach physics. I usually just write if as an abbreviation for efficiency, but just in case you see it in my notes somewhere or in a handout somewhere, okay, I showed you the symbol for it. How do you calculate how efficient something is? Well, it's going to be power out divided by power in. Or work out divided by the amount of work in. Or energy out divided by energy in. And then usually what we do is we multiply by 100 to turn it into a percentage. Is that your formula sheet, Halen? Can you hand it to me? Because I don't think I put this for a reason on your formula. Let me double check. Yep, didn't. I don't memorize this. Here's what I know. If you want me to find how efficient something is, here is the best equation. Efficiency is always the smaller number divided by the bigger number, as long as the units match. Make sure you're dividing watts by watts or joules by joules or whatever by whatever. You see, Zach, in this universe, we know you can't be more than 100% efficient. If you do actually get an answer bigger than 100% and you're confident you've done the physics right, they'll be naming units after you. You'll be winning a Nobel Prize. In fact, probably in about 20 years, you'll be able to buy Bill Gates and Apple because you'll have solved the energy crisis. You'll have all power, no pun intended. That would mean somehow that you would come up with some type of machine that all you had to do is give it a kick and it would just keep going faster and faster and faster and faster, and you can bleed that energy off. You have solved the energy crisis. But in our universe, we say that our universe tends towards entropy. We say in our universe, things are always less than 100% efficient, sometimes way less than 100% efficient. A very inefficient, common everyday item is a light bulb. And unfortunately, politicians have done some bad science. Just this January, I believe, was when they decided now they have phased out incandescent bulbs. Why? Well, read along with me. It says this. A typical light bulb transforms energy at the rate of 60 watts. That's what most of your bulbs are. Most of this energy, unfortunately, is transformed into heat instead of light. About 57 watts go into heat. About 3 watts go into light. Light bulbs are only about 5% efficient, which is true. They're terribly inefficient. And so well-meaning politicians said, okay, well, then let's ban these because that'll save us money. No, it won't. No, it won't. Because your heating bill went down by exactly the same amount of the energy given off by the light bulb. It lowered your heating bill slightly, but it did. It wasn't wasted energy. Certainly not in the winter when you're heating your house. Hey, okay, Mr. Dueck, what about in the summer, Mr. Dueck? You don't want to be heating your house then? True enough. Fair enough. What country do we live in? Canada. What hemisphere are we in? The northern hemisphere? In the summer, in the Great White North, are days longer or shorter? Do we use light bulbs more in the summer or less in the summer? Far less. Well, wait a minute, mister. So we don't, not that big a savings the way you might think. We really don't use light bulbs that much in the summertime, barely at all. Oh, okay, well, wait, Mr. Dueck, what about outside? Unfortunately, these fluorescent bulbs don't work very well outside. We're not replacing, we're not getting rid of those. Those are mostly halogen and other types of bulbs, so you're not getting the savings there. Combine that with the fact that all of these fluorescent bulbs, they have to have mercury inside. Do not throw away those spirally fluorescent bulbs into the trash. You're putting mercury into the environment, and we currently have no technology for removing mercury from the environment, and we have no technology for removing mercury from animals or human beings. In other words, once you ingest mercury, that's stuck in your brain forever at this stage in our technology, and it does bad things. So the politicians were well-meaning. I really don't think they're going to see much savings. I think it's going to be a bigger hassle in the long run. Now, what is the future of light bulbs? LEDs. LEDs are what you have on the back of your camera flashes of your phones. They give off very little heat. They don't have a filament. They use a different technology to generate light. They're nearly perpetual. They last 5 or 10 years. They have really good lifespans. They're almost immortal, not quite, but close. The only problem, and they use very little energy. The only problem with LEDs is they're very, very directional, which is good for flashlights, good for camera flashes, not so good for light bulbs. So 2 years ago, the Philips light bulb company offered an X Prize to anyone who could come up with a light bulb made up of LEDs, but that gave off non-directional light. They offered $1 million. And a whole bunch of different inventors entered that contest, and it was won. Someone won it. Strangely enough, Philips won their own prize, but there are other companies as well now. You can go to the store and you'll see there are LED light bulbs. Anybody bought any of them yet or seen them? They're like $15 a pop. They're pricey. They've got to come down in price. You know what? When they're about $4 a pop, even though that's way more expensive than an incandescent bulb, I'll probably start buying them then, because as I understand it, once I change that LED light bulb, It's good to go for 5 or 6 years, and they use very little electricity and give off almost no heat. Oh, and environmentally, they're not an issue to dispose of. So probably in the next 3 or 4 years, you'll start to see these things here replaced with some type of LED technology. End of rant, but the whole, they meant to do well, they thought they're being environmentally friendly. Please, politicians, talk to physics nerds first before you make these rules. I had to get that off my chest. What uses the biggest wattage? The more heat your appliance transforms, the more watts it requires. A fan uses very little watts because those things can run all day and those motors don't get warm at all. You have 2 appliances that have the biggest wattage, so much so that they have special plugs that run to them. They can't run off of a normal outlet. What 2 appliances in your houses move the most heat and generate or use the biggest wattage? Yep.
Oven and a heater.
Oven is one.
Or like a microwave, a dryer.
Dryer. Okay. Microwaves, they use about 1,000 to 1,500. Actually, a kettle uses about 1,500 watts. Those run off normal plugs. Oven, though, uses way more, unless you have a gas oven, fair enough. But if you have an electric oven, if you ever pull it off the wall, you'll see there's a big, funky, strange-looking plug, and the power cord running into it is like the thickness of your wrist. And I was going to say, unless you have a gas dryer, probably no one has a gas dryer, because gas, when it burns, often also gives off moisture, which doesn't work well for a dryer. Works okay in your oven, because the moisture will still evaporate and get it hot enough that the food will cook, but not so much for a dryer. But if you ever pull a dryer off the wall, you'll see big, funky, special plug. Not for a washing machine, that runs off of a normal outlet. Microwaves run off of normal outlets as well. If you have an electric heat system, furnace, maybe, I don't know, just because I think almost everyone now has gas heat for their furnace at least. Okay. Oh, and the power rating, it's usually printed. Flip an appliance over, look at the bottom, they have to have the power rating. Another appliance, by the way, that uses a great deal of wattage. Girls, in the bathroom, what 2 appliances are you often using that use a lot of wattage? Blow dryer. In fact, any of you that have a house that's older than, let's say, 25 years, if you have a very old house, you may notice your bathroom doesn't have a normal plug. It has this weird, crappy, silver metal looking plug. Anybody have one of those that says razor only? Okay, so you got an old house. Most of the newer bathrooms have what are called ground fault interrupters. They have a little red and black little button right in the middle of the plug. Okay, that's a safety switch. It's designed as soon as you step in water, as soon as there's a short circuit, it'll cut off right away. That's a fairly 15, 20 years or so recent piece of technology. Otherwise, before then, that plug that you have, you can plug an electric razor into it. It uses very little wattage. An electric razor doesn't get warm. You can't run a blow dryer off. You can't run a curling iron. You can't run anything else off of it. Just a razor, barely, because that was also a special plug. But nowadays, most bathrooms have the ground fault interrupter plugs, and you can run significant appliances off of them. We do way more electricity in Physics 12. A 255 kilogram mass is being lifted straight up. You know what? Lifted, that probably means we're doing work against gravity. At a constant speed by an electric motor. It takes the motor 4 seconds to lift the mass to a height of 12.5 meters. Okay. Halen, what's the first thing it's asking me to find?
Find the work done.
Oh, work equals force times distance. Was any work done? We're lifting. We're in the same direction as gravity. They gave me a height. Yeah. It's going to be mgh. It's going to be 255. That's a pretty heavy mass. 255 kilograms. Piano, right? Small piano, not a grand, but small upright piano. G, 9.8. Height, 12.5. About 4 stories. How many joules of work is this? And this gives you an idea of an amount of work that probably a human being couldn't do, because I don't think most of you could lift a piano on your back up 4 stories. You might be able to. Is the door locked?
Yeah.
Wow. I never lock it. Sorry, I didn't know I'd lock the door. What do you get? How many joules of work? I got something totally different. Yeah? Yeah. Yeah. Okay. I'll write the whole thing, and then I'll go to, I guess, 3 sig figs. Anyways, 31237.5. 31237.5, and I'll call that 31,200 joules of work. Most of you are very capable of doing anywhere from 1,000 to 5,000. If you're in shape, maybe even 10,000 joules of work. Much beyond that, not so much. Not so much. Kyle, what's B asking me to find? Hey, our new equation today, power, is work over time. Now, I would have no problem giving you this same question, Emma, not asking you A, just asking you B and expecting you to clue in, I better find the work. Or you could just go force times distance in this equation here. But here I have the 31,237.5. And Kyle, how much time elapsed?
4 seconds.
Okay. That's fairly quick. You're lifting a piano up 4 stories in 4 seconds. This is going to be a pretty hefty motor, I'm guessing. Divided by 4, 7,809.375, 7,809.375. I'll go to sig figs. I'll call it 7,810 watts. Now that's how much power we're getting out. Probably not how much power we're getting in. That would only be the case if this motor was 100% efficient. Things are not 100% efficient. In fact, the hotter a motor gets, the more heat it generates, the less efficient it is. Internal combustion engines, car engines, terribly inefficient. Terrible technology. They give off heat. Oh, the other thing, the louder it is, the less efficient it is. Can you hear car motors from like kilometers away sometimes? Yeah. So not very efficient. Electric motors are the future. This one here is an electric motor, apparently. C. Manny, what's C asking me to find? Okay, we said efficiency was equal to smaller number, power out divided by power in. Let's write that. Power out divided by power in, and then we'll go times 100 at the end to turn it into a percentage. I just remember smaller number. You know what? The power out, we are getting 7,809.375 watts out. And it looks like we're putting 12 kilowatts. How many watts is that? 12,000 watts in. Mr. Dueck, how would they be getting 12,000 watts? I don't think power outlets give that much. No, power outlets usually have 120 volts, but you can step up voltage using an electrical device called a transformer, not the cartoon characters that you're thinking of. It's an actual electric device, and therefore you can get more wattage. .65 times 100, 65.1% efficient. Okay, the other 35 or so percent is going into heat and noise and other dissipative energies. Mostly heat. Next one. A girl pushes a, I don't know why I wrote that in scientific notation, probably because I wanted to go to 2 sig figs, a 300 Newton box along the floor for a distance of 4 meters. The coefficient of kinetic friction is that. She then lifts the box straight up. What's the minimum amount of work she's done? Okay, work. Well, you know what? I think the total work is going to be the work she does by lifting and the work she does by sliding. I know the question says she's sliding first, but that's going to be trickier to find, so I wrote that Kai last. Kai, work is what times what? So the lifting work, I think, is going to be, well, when you're lifting, hopefully you've spotted this trend. Which force are we always doing work against when we're lifting? Okay, so the lifting is going to be mgh plus. Now the sliding, What are the forces acting on this box? Get the obvious one. What else? Here's the applied or the slide force. Because I said minimum amount of work done, Emma, I think we're going to assume that she's exactly matching friction and not putting any more force. In other words, applied isn't bigger, isn't smaller. It's exactly the same. That's why I added the word minimum. She could be pushing harder, in which case she could be tiring herself out even more. But for now, minimum, Jake, would be, force times distance. Which force? I don't know the applied force. Oh, but look. I know another force the same size as the applied force. Which one? Friction. So this is going to be which is going to be mgh plus, hey, friction is what times what? I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Mu mg times the distance. Okay. I got lots of room. I think I can go here. mg. Oh, you know what? I didn't give you the mass. I gave you mg, didn't I? Because I gave it to you in newtons. So 300, don't multiply by 9.8. We already did. H, 1.2 plus mu, 0.33, mg, 300, distance, 4. That's why I tend to use h for a vertical height and d for a horizontal distance, just in case I have two distances in the same question. A little easier to keep track. Hey, what's the minimum amount of work she did? There's the lifting. There's the sliding. Do you all get 756 joules? Or am I wrong? Yeah. 756 joules of work. She may have done more, but she had to do at least that. Dane, what's B asking me to find? Efficiency is, this is how much she expends. Now, I'm not sure what's in and what's out because they didn't use the word power or energy in or out. You know what? It's the smaller number divided by the bigger number. It's going to be, I guess we're getting out 756 joules, and I guess we're putting in 1,200 joules. She's 63% efficient. Where'd the other 37% of her work go? Honestly, friction heated up the floor, most of it. And if you don't believe me, try even on your lab tables, press down, run your hand really quickly. You'll generate enough heat to almost burn your skin, right? You can get a rope burn off these, a fairly nasty one. Yep, okay. That, and all that heat, that energy's got to come from somewhere. It's coming from you. Oh, in industry, how do we reduce friction in industry? What do we do on almost any machine or part? Yeah, we grease them up. Okay? Absolutely. Absolutely. I think it's the last one. Yes, it is. On a stair climber at the gym, a 58-kilogram person lifts their center of mass up 18 centimeters. Nice try. I was doing so good. Please come back. Okay, pen's back. 18 centimeters. Nice try. Of course, 0.18 meters. Oh, and 10 minutes. Nice try. 10 minutes in your head. How many seconds, please? 600 seconds. Okay. And their muscles are 20, they take 500 steps in 600 seconds. Their muscles are 20% efficient. Find the rate at which the person does work. What are they asking me to find in part A? That was the definition I gave you in English in the very, very beginning of the lesson. I said power is the rate at which we do work. So power, which I guess is work over time. By the way, there are other equations for power because work over time doesn't exactly explain, hey, what's electrical power? It turns out for electrical power, it's the voltage times the current, which I guess tells you that voltage times current is the same as work over time. Yes, it is in a roundabout way. Anyways, force times distance over time. On a stair climber, which force? Stairs, which force? Okay, it's going to be mg. You know what? I think it's going to be 500 stairs times each stair. I think that's the total distance, is it not? Because technically your displacement on a stair climber, your displacement is what? 0. You're not going anywhere. Okay, but distance, we're picking our words carefully. 500 steps would be 500. In how long? Okay. How many watts of power has this person generated that the stair climber had to absorb somehow? $58 times 9.8 times 500 times 0.18 divided by 600. Do you get 85.3? No? Yeah? 85.3 power is measured in what? Watt? Watt? Power is measured in watt? Okay. Oh, yeah, the jokes just keep coming. Now, that's not how much energy or how much power this person burned, though. The nice thing with exercise is our bodies are not very efficient, which means we burn more energy than we actually accomplish on the machine. Where does most of it go? Hey, you sweat, heat, right? So B says, find the rate at which the person uses food energy. Now, what have they given me here? They've given me the efficiency. The efficiency is where the power out is the 85.3. Power in is, hey, that's the power that your body has used up the food at, the rate at which your body has used up the food energy at. So I need to get power in by itself. Where is it right now? Bottom. You know what? Let's multiply it to this side. At the same time, I think we can divide that there. Yeah, we're doing some cross multiplying with a vengeance. I think what we can say here, I hope, Valoria, is power in is what you got out divided by the efficiency. What I really want you to realize, Kai, is there's 1, 2, 3 things here, and as far as I'm concerned, I can give you any two, find the third. Usually it'll be out and in, find the efficiency, but hey, sometimes I like to go the other way around. So it's going to be 85 point, you know what, let's use the full value, 26 divided by 0.2. And I get 426.3 watts. How do you know it's watts, Mr. Dueck? Because we're dealing with power. If it had been work, my units answer would have been in joules. Okay? We need to practice this. I'm going to give you a bunch, but I'm trying to give you 20 whole minutes to work on this. Here's what I assigned my other class, my block B's, with the lesson that totally stopped working partway through, and then I could no longer continue with my, you can see I tried typing occasionally, and it just wasn't working because too much physics. One, in the first section, 1, 2, 3, 4, 5, 6, 7, so skip 3. And then the mix-up questions, 1, 2, 3, 6, 9. So let me do that over here. I said in the first section it was 1, 2, I said skip 3, 4, 5, 6, 7. Some of these are tricky. And then what did I say? 1, 2, 3, 6, 9. Is that what I said?
Yes.
3, 6, 9. I made it through the lesson. Yay, my pen sort of worked most of the time. Pause.